Hello again. This is Math 2232 coming to you from the College of DuPage. The title of this lecture is Applications of Series Continued, Binomial Theorem, and Composition of Functions. As always, please be an attentive learner while watching this video. By way of introduction, infinite series forms a rich subject, and in COD Calculus 2 we cannot do it all, but here are a few more highlights, and only some of the many highlights that exist here. We begin by revisiting the binomial theorem, this time with a broader scope of exponents than you studied earlier in your pre-calculus days. And this, in fact, we'll see leads to an infinite series representation. And this work was done by Isaac Newton himself. And to fully appreciate this work, we briefly review the binomial theorem as you studied it in your pre-calculus studies. There you learned, if n is any positive integer, then a plus b whole to the n is equal to the summation from I equal 0 to n of the binomial coefficient n, choose I. And then we had a, the powers of a in decreasing order, and the product of that with the product of b's in increasing order of exponents from 0 to n. And so it would look like this when you expanded it. And the general form of the binomial exponent was this calculation, and n choose 0 was known to be 1. Now, in COD pre-calculus, we usually prove this by math induction, but this is a nice combinatorial proof. You see, a plus b whole to the n is equal to a plus b times a plus b n times. So if we repeatedly use the distributive property, we see that there is a term that is am b n minus m, where we chose m of the n terms up here, m factors, to contribute an a to the term, and then after that the remaining n minus m terms of the product contribute a b. So the coefficient of this is the number of ways that we can choose m objects from a set of n. And that is n, choose m, the binomial coefficient, which is defined this way. So when we expand this to all possible values of m from 0 to n, we see that this sum is equal to this, as claimed in the theorem. Let's use an example of this earlier theorem. So here we're going to use the binomial theorem to expand 2x minus 3 whole to the 4th power. Now here the role of a in the theorem is being played by 2x, and the role of b in the theorem, notice there's a plus sign there, is being played by minus 3. So we substitute in and do some simplification. So 2x minus 3 whole to the 4th is this summation. This is playing the role of a, that's playing the role of b, and then we write this out because we were supposed to simplify this, we were supposed to fully expand it. So we expand it and do the calculations, and we get this as an answer. It is instructive for you to actually go through and verify this calculation, but here we see that there are 1, 2, 3, 4, 5 terms in our expansion of this to the 4th power. This is a theorem that Newton proved. If k is any number, it doesn't have to be an integer, and if the absolute value of x is less than 1, then 1 plus x whole to the k is equal to the infinite sum from n equals 0 to infinity. This is k n x to the n. Now this is then what we get for the what k is. So you start with k minus 1, k minus 2, all the way down to k minus, and that's k minus the whole of n plus 1, and when you distribute it you get this. This is all over n factorial. And again, k0 is 1. Now, if k is a positive integer, then you'll start here, and eventually you'll hit k, you'll have a 0, and 0 the rest of the way, so the series is finite. So in the case where k is a positive integer, this is exactly the binomial theorem that we were talking about. But what Newton showed, and what we will show, is this works for k not a positive integer. And the sum becomes infinite because you never hit 0 in this multiplication. Well, it fits nicely in this chapter because if you take 1 plus x and use an exponent of alpha, and you find the Taylor series about x equals 0, and let's just do that. So you take a bunch of derivatives. Here's the 0 derivative, of course, first derivative, second derivative, and the nth derivative is going to look like this. Now, at this stage, it gets really cumbersome to write this product down, so we're introducing some notation that Donald Knuth, the godfather of computer science, invented, but he said, call this alpha to the n underscore, and you get this. So that notation gets used here a little bit. So what we have is, I'm calling that one alpha to the n underscore, and this is 1 plus a, and then this is alpha minus n. Now, since we're doing the Taylor series of this about x equals 0, we substitute x equals 0 into there to get these values, and we divide each by n factorial, and we take this times x minus 0, and you see we get f of x is equal to, or we get that the Taylor series is equal to this. But now we can say, what's the radius for convergence for this series? Well, our friend the ratio test comes to the rescue. We take the limit as n goes to infinity of this. Again, the x is included there. We write what all these things are, and many things will cancel, and you get this. So it's the limit as n goes to infinity of alpha minus n all over n plus 1, and this is the absolute value of x, which I can jerk through the limit as we always do, and this is absolute value of x times the limit as n goes to infinity. This is alpha, which is a fixed constant, minus n over n plus n. And so you can divide top and bottom by n, and you can conclude that this limit is 1. So this concludes whenever, this converges rather, whenever the absolute value of x is less than 1. So the radius of convergence is 1. And it can be shown that for some values of alpha, we can have an interval of convergence including the endpoints. I'm not going to show that here, but that's actually not too difficult, and the earnest student may want to explore that as well. Now it remains to show that this Taylor series converges to the left-hand side function, which ends up being the 1 over, or it was the, let's see, it is 1 plus x whole to the alpha, but it can be shown that the remainder here goes to 0 for some t in this interval, and similarly you can do it for t on the other side of this between 0 and minus 1, but I'm choosing not to cover this proof in the video. It's several pages, and I think our time is better spent applying this theorem than studying the proof. Let's do an example. Here I ask you to write down the first 4 terms of the binomial series for the square root of 9 minus x. Well, in this case, k, the exponent, is 1/2, and we need to rewrite the term a bit to put it in the form required. So the square root of 9 minus x, I can factor a 3 out of that, and then this is going to be 1 minus x over 9 whole to the 1/2, and just to make it look exactly like the theorem, this is 3, and this is 1 plus, this is minus x over 9 to the 1/2. So then I use the theorem to expand it. So this expression, the 3 just sits here, but using the theorem on this, I get the summation n equals 0 to infinity. This is 1/2 n. This is minus x over 9 to the nth power. So then I go through and I write the first few terms of this. The 3 just sits there. When n equal 1, I'm going to get 1. when n equals 0, I get 1. When n equals 1, I'm going to get 1/2. When n is equal to 2, I will get 1/2 times minus 1/2 over 2. When n is 3, I will get 1/2 times minus 1/2 times minus 3/2 over 6 times this to the cube, and so on and so forth. And when I simplify that and I distribute the 3 across, I get 4 terms that look like this. 3 minus x over 6 minus x squared over 16 minus x cubed over 3, 8, 8, 8. Again, a very possible problem for me to ask along the way. Let's look at a second example. Find the power series for this function. This is going to be the cube root of 1 plus x. Well, this time k is going to be 1/3, and so we can write this in this way. And actually, I wanted to find the whole power series, and I just guess I do ... here, but I just plug in things with k equal to 1/3, and you should check this. And by the way, for this value, k equal 1/3, you can prove that it converges at the endpoints. So we have convergence from -1 all the way to 1 of this. And it would be good practice to write this as a summation of something. Now, we've talked a lot about Taylor series, so there's a summary in your book. Now, I took this from a different book, but this is very similar to page 654 in our textbook of reference, so you should look at page 654. That makes you think of a factorial, doesn't it? The beginning of a factorial. So anyway, you have a power series for a whole bunch of functions. Now, because the convergence is so strong, that is, it's absolute convergence, we can not only differentiate and integrate term by term, as we talked about in the last lecture, but we can also substitute expressions into these power series and have far broader results that are very similar to substituting composition of functions, doing that with polynomials. So let's look at this list, not exhaustively. You really should be able to derive everything on this list from basic principles. That would be good practice for your final. But let's look at just a few of these. This one way down here, and I wrote it a little bigger up here, is actually Newton's binomial theorem. So you see 1 plus x to the k is all this business, and it shows it converges from -1 to 1, but then they got a little footnote that says it depends on the value of k, and we talked about that a bit. So again, we've done several examples of this. We won't belabor it, but yes, that's in the list. Another thing that's in the list is our expansion of sine. Now you remember that I could have called this sine of z. That could be a dummy variable, and we get the odd powers, and they're divided by factorials, and it's an alternating series, and this converges for all real numbers. Let's apply our composition of function result to this. So think about this as being sine of z, and we'll go to do a problem. Find the Taylor series about 0 for sine of x squared. Well, here x goes to x squared, and then you take the sine of that, so the z here could be x squared. Now you could do this from basic principles, taking these derivatives, but if you start taking these derivatives, it gets very complicated. So you're a lot better off to take the series for sine of x and just substitute in x squared in for x. So x becomes x squared. X to the 5th over 3 factorial becomes, actually that's x cubed over 3 factorial, becomes x to the 6th over 3 factorial. Instead of x to the 5 over 5 factorial, that becomes x to the 10 over 5 factorial. Instead of x to the 7th, that is x to the 14th over 7 factorial plus ... Pretty cool, huh? A significant improvement in efficiency and getting to the correct answers much more efficiently by using composition of functions. Another function that you should know about, expansion, is the one for cosine. It's shown down here. I made it bigger up here. And again, this converges for all values of x. So this is a very powerful form of convergence. And again, the cosine is going to be the even powers. Again, it alternates and it's divided by these factorials. Let's test this using our composition of functions. So here I say find the power series for cosine of square root of x. So here is what the cosine of x was, but now we're replacing x by the square root of x. So instead of getting x squared, you just get x. Instead of getting x to the fourth, you get x squared. Instead of getting x to the sixth, you get x cubed. And instead of getting x to the 8, you get x to the fourth. And again, you see we're dividing by this. And this converges for all x in the domain of this cosine. And again, you do have to worry about the domain when you do composition of functions. But this converges for all x bigger than or equal to 0. Make sure you understand these examples. Let's look at another one. Here is an expansion. Again, you can derive all these yourself. Here's an expansion for the ln of x. And since the L of x is not defined for x equal to 0, we're not expanding it about 0. We're expanding it about 1. But you see that the natural logarithm of x can be found to be this. Now notice that this is an alternating series. We get plus and minus 1s, and we get this for our expression. And this is what it looks like. Blown up just a little bit, and the convergent here can be shown to be between 0 and 2, but 2 is included, and that is very important for something we're going to talk about just in a minute. So 2 is included. Again, this would be a great exercise for you to go through, but we're just going to apply it here. Okay, now this is what we had as a result, and I'm just going to substitute x equal 2. And again, it converges for x equal 2, so that was fine. So on this side, we get the natural logarithm of 2 is equal to, and when we substitute 2 in here, all of these x minus things are going to be 1. And so this whole thing, if you substitute x to be 2, is the alternated harmonic series. So you see, I've proven, as I promised you I would, that the alternating harmonic series, we knew this converged already from the alternating series test, but now we know what it converges to. It converges to the natural logarithm of 2. Let's look at another example. And again, you could develop this yourself from basic principles. In fact, I may develop this from basic principles. You could just go through and actually compute that, but I think I'll derive this from a different thing, a different approach, which will be useful. But this is also an important result. So the arctan of x can be expanded this way, and this is for x between -1 and 1. The endpoints are included in this convergence. Again, there's a whole wealth of things that you really could practice using this table. But let's apply this then. In fact, I think I'm going to actually derive this for you in a way that you might not be thinking about. Okay, now there was an earlier chapter where we studied the harmonic series, and then in a lecture that followed that, we morphed things that looked like the sum of the harmonic series, not harmonic series, geometric series, excuse me. I'm talking about geometric series. So we know that a geometric series converges to the first term divided by 1 minus r. And we learned that g, even if we don't have exactly that form, we could write this as 1 over 1 minus a minus x squared. Now then, and this is going to be the summation of the r squareds, and so this can be shown by doing that 1 minus a minus x squared. That this ends up being the geometric series for this. So it is an alternating series, and this is x to the 2n. But now, since this converges so strongly, I can integrate it term by term. And I'm going to integrate it from 0 to x. And I'm going to start calling this variable u here, just so it's not confusing. So if I integrate this from 0 to x, I get the arctangent of x, arctangent of u evaluated at x and at 0. Now the arctangent of 0 is 0, so those drop out. So this is the arctangent of x. But if I then integrate this term by term, what will happen is I will add 1 to the exponent and divide by the new exponent. And so this is what I get for the arctangent of x, is this infinite sum, which is exactly the one that we saw up here. Now, the application of this, that's a very powerful application. This is true for everything, including 1. So if I put 1 in here, the arctangent of 1 is pi over 4. And I put 1 in here, so that means that pi is 4 times this alternating series here. That means that we can provide a way to estimate the value of pi as accurately as we care to estimate it. Wow. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.